So everybody, welcome to today's Ask an Expert session. Today's subject is the Intel Nios 5/G processor. So for today's session, we have Rod Frazer, which is our expert for today. He is an embedded technology specialist FAE with Intel PSG for over 20 years and over 35 years of industry experience in the embedded systems, hardware, and software development space. Supports customer designs with the Intel Nios processor, SoC-based FPGA devices, and all of Intel FPGA tools for embedded development. Thanks for being with us today, Rod. Yes? I see someone. Thank you. Thanks for being today with us, Rod. And the other expert is me. I joined Intel FPGA training team in 2022 at GDC, which is Guadalajara Design Center in Mexico. I have a bachelor's degree in electrical engineering with biomedical engineering focus, and I am a subject matter expert in the Intel FPGA training group for teaching and developing training on SoC FPGA devices, also Intel Nios 5 processor and other training courses. Thank you so much for the invitation too, and I will be today's moderator. Please, this is your session, and please also participate. Feel free to ask by voice. You can unmute and then ask any questions you have, or by chat. I will be attending also the chat. Enter your question, and we will relay it to our expert today. So feel free to participate. Okay, so a little bit about our ground rules, and then we will move on to the session. Any question you can think about Intel Nios processor 2, 5M, or 5G is fair game. Over the phone or your mic and in the chat. If it's a detailed design-specific question, we'll try to answer if possible based on your description. Hopefully your questions can be answered in a reasonable amount of time during the session. If not, we'll try to follow up with you after. We want to get in as many questions from as many folks as we can, just to make sure that everyone gets a chance to participate. We may point you to your local FAE for further assistance in case we cannot resolve the question during the session. So moving on, I'll give the presentation for this presentation space for Rod. Please, Rod, go ahead.
Okay, and I'll just let you know when to flip slides. That works for you, right?
Yes.
Okay. All right, so what we're talking about today is the new Nios 5G processor that was rolled out in the 23.1 tools a few weeks ago. So what we're not really mentioning in this slide deck is the fact that Nios 5M has been in the tools for about a year now. And so this represents the second variant of a Nios 5 processor that we're actually putting in the tools. The G stands for general purpose processor kind of thing, whereas the M for Nios 5M stood for microcontroller kind of a processor. So the Nios 5G would be expected to be a little bit bigger, a little bit more capable processor than what the Nios 5M was. And if you look at the list of bullets on the left here, it's still a 32-bit general purpose processor. It uses the RISC-V RV32IMA instruction set architecture. So the way that differs from the M core is that M letter in the ISA designation, and that M letter specifies that you have hardware multiplying divide integer arithmetic available in the core. So that's what the, from an ISA set perspective, it's identical to Nios 5M, except that we add multiplying divide, so it becomes an RV32 IMA architecture device. And the RISC-V compilers are really good about, having the variants for the RISC-V instruction set in them. And so you basically use the same cross compiler for this G core. You just pass in a flag that says, hey, I've got an IMA extension instead of just an IA extension. This is supported in our Pro Tools today, so it supports all the device families that are available in the Pro Tools, like Agilex and Stratix 10 and Aria 10 devices. It should be available in standard tools in a future release of the standard tools as well. Added to the Nios 5G above and beyond what the 5M had are custom instructions and an instruction and data cache, and as I said, the integer multiply and divide capability. So those are kind of the first features that come in the G. There'll be a release later this year that adds some extra features to the Nios 5G processor, which will bring in ECC support and tightly coupled memory support and a floating point unit capability that you can turn on optionally. So the G core kind of makes its presence in the 23.1 tools, and it'll kind of get added to a little bit in a future release here later this year. And along with the 5G, we're adding support for FreeRTOS and Zephyr RTOSs that can be run on either Nios 5G or Nios 5M, actually. So those are kind of new features in the 23 tools as well. If you look at the block diagram in this slide here, the instruction and data cache on the right side, those are things that have been added that did not exist in the M core, and that integer multiply divide hardware block in the bottom right corner of that processor core block is also represents the hardware multiply and divide. Then on the left side, the custom instruction block is what the custom instruction feature was that was added to that. Other than that, this is very similar to what the Nios 5M core looked like. It still has the same debug module, the same AXI instruction and data masters, and the same interrupt structure and reset structure. So it's primarily in this initial release of 5G, it's the custom instructions, the integer multiply divide, and the instruction and data caches that you see in that block diagram. So I think maybe let's go to the next slide. So when you parameterize the Nios 5G core in Platform Designer, this is what the parameterizations look like. It's kind of like the top part of the parameterization boxes on the left side of the screen, and then they pasted the bottom part on the right side. And what you can basically see here is it's allowing you to configure the reset logic that you want the core to support, where the reset vector is, what the data caches and instruction caches are that you'd like to configure, and how many peripheral regions you want to set up for non-cacheable space. So peripheral regions basically equate to non-cacheable I/O space. And then on the right side, we show you what basically the bottom section of the parameterization window is, which is where you can define any custom instructions that you'd like to define for the architecture. And we'll get into more detail about what all these things mean in future slides here. But this is the here. So maybe the next slide. When you look at the caching and peripheral regions customizations that you can do here, these are basically your options. If you look in the table kind of in the bottom left here, you can see the 5G supports cache sizes from 1 to 16 kilobytes for both the instruction and data caches. These are similar to what Nios 2F had, although Nios 2F actually allowed you to turn off the caches. We don't actually allow you to turn them all off. You have to start with a minimum size of 1K, and you can grow these up to 16K. Something that is different, although Nios 2 actually had a way to mark a peripheral region as well, but in the RISC-V architecture here, the way you define where things are not cacheable in the address map is by turning on one of the two peripheral regions that we define here in the GUI. And these can be anywhere from 64K is the smallest window size you can make, up to 2 gigabytes. Like I say, basically the idea here is that if you're going to have peripherals that need to have non-cacheable read and write, operations made to them, you're going to put those in a memory span that you can wrap around a peripheral region. You can have up to 2 defined in the system, so you don't have to put them all in one spot, but you can have up to 2 spots that you put these peripherals in. This can also be used for if you've got like let's say you want to have a piece of non-cacheable RAM. You could actually use a peripheral region definition to just mark a portion of your RAM as non-cacheable as well if you wanted to do something like that. So if you don't turn a peripheral region on, you get an error warning kind of a thing that shows up at the bottom of this slide here, because you know, just having a Nios 5 processor come up with an on-chip memory and run a program out of it is not that interesting. It's legal, you could technically do that, but it's not that exciting. You can't really interact with the external world, so it doesn't really make sense to create a Nios 5 system that doesn't have a peripheral region defined when you're talking about a Nios 5G core here, because typically you're going to want to interact with some I/O, and that's going to require a peripheral region. So maybe let's go to the next slide. Yeah, I think you got to dump the laser pointer to get it to move. If you, there you go. So since
Sorry,
we now, yep.
Rod,
Go
there
ahead.
are a couple of questions in the chat. That's why
Okay.
I was struggling with the pointer.
Okay.
So it says we use Cyclone 10 and plan to use FreeRTOS with Nios 5. I'm wondering if there are plans to port the FreeRTOS TCP stack, or if there's another stack already ported and available or recommended.
So we'll have a slide that comes up on this later, but it doesn't quite address the entire question there. FreeRTOS itself has been ported onto Nios 5 and Nios 5M, but that's really just the kernel. To my knowledge, nobody has built an example up that would run the FreeRTOS TCP stack on any kind of example design that we have with one of these cores in it. There happens to be a micro COS 2 example with the micro C TCP stack enabled that runs on a piece of example hardware. If I were recommending what I would do if I were in that situation, I would say, if you want to run FreeRTOS, run FreeRTOS, but I wouldn't look for another stack. I would just get the FreeRTOS stack up and port it onto that platform. Well, I don't think we have an example design that demonstrates that today, but I think that would be the path of least resistance for you to ultimately go there.
Thank you for your answer. And there's another question from Richard Ross, which says, will Nios 5 be open sourced like most other RISC-V cores, and how might it be used with eASIC-based design?
So the answer is no. It won't be open sourced. It's more of a commercial offering that we provide. We happen to use the open source definition of RISC-V to implement that, though. And so, like, if you look at the source code that gets generated by the platform designer tool after you instantiate a Nios 5G core, it'll be encrypted. So you won't have visibility into the actual source for the core. And as far as using it on an ASIC, I could make the argument that you'd be better served going out and actually getting a core designed for an ASIC, because the Nios 5 cores are very heavily optimized for FPGA deployments. And so we're making design choices and trade-offs based on having to crush this into resource-limited FPGAs. And if you're going to go down an ASIC path, an ASIC has miraculously more, resources available to it. And you would probably want a core that is more geared toward ASIC deployments if you were going to do that.
Now, I'm sorry. I asked about eASIC, which is the partner organization in PSG, not an ASIC. eASIC requires Verilog or VHDL. Thanks.
Yeah. So if you're going down, as I was going to say that next, if you're going down a structured ASIC path like eASIC, then yes, that does actually make sense to use a Nios 5 in those kinds of applications. And they should, just like you've been able to put Nios 2 cores in eASIC devices in the past, you should be able to put Nios 5 cores in eASIC devices from this point moving forward into the future. So that actually does make sense. And we would work with you to try to enable that to happen. You should be able to put the Nios 5 core down and have a debug interface accessible to it, so that you can actually run debug sessions from an external host debugger and stuff like that. That actually does make sense. Back to what I was saying about true ASICs, though, Nios 5 wouldn't make sense in true ASIC forms, but in structured ASICs like eASIC, it definitely would make sense. And the reason why I say that is because in theory, what you're doing with eASIC design is you're prototyping in an FPGA, and then you're trying to just migrate that kind of as is over to the eASIC design. And so that's a flow that we've kind of supported for forever. And it does make sense still using Nios 5. So I think, thanks for the clarification, though. All right. So
I think we can continue. Yeah.
Okay, great. So I was talking about the cache capability that's introduced with Nios 5G. And so since the hardware now supports caches on both the instruction and data pipeline paths, there are the need now for cache maintenance operations to do things like flushing and invalidating those caches. Nios 2F had the same requirements. And so if you look at how we've implemented this in Nios 5, it's basically taking the same how function calls that we had for Nios 2 and implementing them for the Nios 5 specific requirements. So there's functions that will do flush and invalidate of the data cache, like alt dcache flush. And there's a invalidate only, so it won't write back, but it'll just invalidate. That's an alt dcache flush, no write back. And then there's a couple of instructions you can use to invalidate the instruction cache. The one thing that I would point out with the instruction cache is when you invalidate the instruction cache, it always invalidates the entire cache. We support the alt icache flush function call there, but the reality is it'll flush the entire cache just like the other one does. I don't know if in the future we'll actually be able to have a cache line flushable instruction cache, but today in the first cut of Nios 5G, when you flush the instruction cache, it's an all or nothing thing. But so we have cache maintenance operations that show up in software in the HAL space as well here. So maybe next slide. I think we're gonna get into this is just pointing out that the multiply and divide operations that get added, they basically go into the ALU, the arithmetic logic unit of the processor. So the ALU is where you have things like the arithmetic, relational, logical, and shift operations defined by the RISC-V instruction set. So we basically add RISC-V compliant multiply and divide instructions to the ALU. And these just allow the processor to have higher performance when it's running through software that can benefit from multiply and divide operations. Those don't have to be emulated in software routines anymore. They can just be executed in single instructions. And maybe let's go to the next slide. So we're going to start talking about the custom instruction capability in Nios 5G here. It can technically support 4096 user-defined custom instructions, but there's a bit of caveat to that, and we're going to get into what that actually means in the next few slides. But if you just want to know, okay, the maximum number of possible instructions is 4096. In reality, it's probably a lot. You probably think about it as a lot fewer instructions. That probably somewhere on the order of 32 is a practical limit there. But I'll show you how we get that number of 4096 at the end of the day. And basically what the custom instruction capability does is it allows the ALU in the 5G processor to have direct access to hardware implementations of whatever logic functionality that you'd like to bring. So your custom hardware operations can appear to the processor and be invoked by the processor by native instructions in the processor instruction set. Okay, now this is typically used to try to bring performance or hardware acceleration kinds of things. People use these on Nios 2 for various kinds of things. Sometimes it's just for abstraction and security kinds of things that they build into it. But it's any kind of a thing that you could think of that you might want hardware to be able to perform for the processor that the processor can't do natively in its own limited ALU. And sometimes it's just a simple thing of instead of doing one multiply, you're doing 10 multiplies, or you're doing an entire matrix multiplication on some collection of data somehow as an atomic operation or something like that. The custom instruction interface on Nios 5G is very similar to Nios 2, but it is not compatible. So if you have a Nios 2 compatible instruction, like a custom instruction from Nios 2, you can't just drop that into a Nios 5 custom instruction. The architecture for the Nios 5 custom instruction is different because of the RISC-V architecture that we're plugging into. So they're very, very similar, but they are different. And if you had a Nios 2 custom instruction, you'd have to port it over to Nios 5 to get it to work right. Let's go to the next slide. We'll get into more details on this. So this is what an instruction opcode looks like in a RISC-V world here. And what I kind of just want to point out here is there's the names of these fields are func7, which is basically, func7 is some extension bits that tell instructions how to do something a little bit differently than the native instruction or the native thing would have done. And so, like, if you look at the table below, you can kind of see like how they have like, add and subtract are basically the same opcode, but they have a difference in the way func7 is encoded, which is what tells the instruction whether it should be doing an add operation or a subtract operation. Okay, so func7 is just kind of a instruction modification field. Okay, and then you've got the RS2 and RS1 fields there, which are the register sources for the first and second operands. So the way any instruction works is it can take 2 operands out of existing registers, and there's 32 registers. So the source register could be any of 32 registers there. That's why those are 5-bit fields. And then it produces a result that lands in the destination register, which is that RD field. Okay. Next to the RD field, there's that func3, which is 3 more bits that are kind of like func7, which is just modifiers to the opcode that kind of tell the instruction how to do things a little bit differently. And then the last field is that the opcode field itself there. Okay, so this is what you have to work with, right? This is what an instruction basically looks like in RISC-V. And so when you think about custom instructions, the RS2 and the RS1 and the RD field, we really can't change those because those are just the source and destination registers. So our custom instruction will be taking the source contents from whatever those registers are encoded with, and and the result that we produce will wind up going back into the destination register that's defined by the instruction. So we can't really manipulate or do anything with those. The ALU controls all of that for us, but the encoding of the opcode and then the func3 and the func7 field, those are the bits that we can actually customize and use to make our own custom instructions out of. Okay, and so let's maybe go to the next slide, and we'll get more into detail of how this actually gets implemented. So if you look at the block diagram on the right, this is just trying to show how like the normal ALU, which is kind of like this big mux block that they drew here, that's where your normal operations are that the ALU has in it. So your add, subtract, multiply, divide, shift, rotate, compare, and things like that. Those are in the ALU. So basically what your custom instruction can do is it can have access to the inputs that would come into the ALU, and the result can be passed back into the destination register by the logic that would route the result of the ALU into the destination register. Okay, so that's what conceptually what you're doing when you insert a custom instruction like this. If you look off to the left here, I'm just trying to think if I want to add anything. So the words over here are talking about how the custom instruction blocks are added to the ALU unit. That's kind of what the block diagram on the right side shows. The way we figure out, trying to think of how to word this, we basically create a topology where, based on the opcode and the func7 upper 3 bits, we come up with a way of breaking out a demux to 32 unique blocks of hardware. And so what I'm trying to say there is our custom instruction facility within the Nios 5 processor basically allows you to hang up to 32 unique data paths off the ALU that we pre-decode inside the processor. Okay, and so that's made up of 4 opcodes. Okay, so out of all of the opcode space that's defined, okay, I forget how many bits it was around 8 bits or so, right? So out of the 128 or 256 opcodes that are defined, 4 of them are pre-allocated by the RISC-V architecture as custom instructions. Okay, so you have custom 0, 1, 2, and 3. There's only 4, so technically there's only 4 custom instruction opcodes. Okay, but we take the upper 3 bits of the func7 field, and we use that to create up to 8 decodes off of each custom instruction. So when you think about it, we can do 8 times 4, which is actually 32 unique data paths that will route out of the ALU into your custom logic block. We're pre-decoding that for you. Okay. Now, like I said in the previous slide, we were talking about what the whole format looked like. There's actually 4 more bits of func7, and there's 3 bits of func3 that we haven't talked about here. Okay, so those bits of func7 that we haven't used for our predefined decode are available in your custom instruction, and you can do further decoding of those in order to break this down into more information that you can choose to, how to make your instruction work and do what it wants to do, which is how you get up to that whole 4096 number that we had in the previous slide here. Okay, so this block on the bottom left is kind of showing you, it's not showing you the full 32 breakdown, but it's showing you you've got 4 custom instructions that are decoded by the ISA itself. And then off of that, we're using the upper 3 bits of Func7 to decode down into 8 more discrete data paths that we pre-decode for you. Okay, so let's maybe go to the next slide, because it shows what the next level of this looks like, what the next level decode looks like. So the block on the left is what was on the previous slide. If you look at the block on the right, what you see is inside the custom logic block, it's the yellowish block on the left, we're showing that inside there you can take the 4 bits of Func7 that weren't used by our decode and the 3 bits of Func3, and you can further use those to get another potentially 128 decodes of, custom variations that your custom logic block will implement there. And if you can treat these however you want to. They can just make the logic itself operate differently, or it can actually, you could have yourself decoding back out to, different, sub instructions that you're actually deploying inside your custom logic there. But so this is how this is kind of comes together, and how you get to like this 4096 number of possible custom instructions. It's actually the combination of the 32 discrete decodes that we will do in our hardware inside the Nios 5G core itself on the left, plus the extra decode that you could do in your actual custom instructions, which is what we're trying to show on the right here.
I think there's a question regarding the ALU. It says Nios 1 or 2 was based on full identity of form Z, or, and then puts a parenthesis X and not Y to get and or. Do you use this in Nios 5? I don't know if you maybe can take a look at the chat window and see what it's about. We can try and answer.
Yeah, that's what I was going to look.
Yeah. And then there's another question, maybe. It says there's a simple way to replace the HAL framework with my own CRT0S. Device drivers make file linker script.
So, okay, let me try to answer this first question.
Okay.
It's saying the ALU on Nios 2 is based on the identity of form. Let's see. I don't know the answer to that question. I would have to think about this. I'm not so sure.
Is this probably we can get a little bit more of insight from Richard? Ross, sorry.
Would you like to or not?
Yeah.
So most of the time in other in RISC-V and others that you do a whole bunch of operations, then you have a big multiplexer to choose versus AND or XOR, add or subtract, as your diagram shows. The Nios 1 inside maybe did add a subtraction or addition on, let's say, the left micro ALU, but on the right it did the function X and not Y, or it might have been X or not Y. And by XORing those two and either adding something, you can generate the AND instruction and the OR instruction, or the X and the XOR instruction without as much multiplexing amongst 5 or 6 different operations.
Yeah.
It was just a really one of the coolest identities I've ever seen. The ARM one might have used something similar, but the Nios 2 was just beautiful. So just wondering if you used it in this one, that beautiful identity in your current ALU.
Yeah. I don't know the answer to that.
Okay.
I'd have to look into that. Yeah, off the top of my head, I don't know how they implemented that.
Okay, thank you anyway.
Yeah.
We can circle back. Yeah, no problem.
Yeah. The other question though about the HAL framework and being able to replace the CRT0 and your device drivers and the make file and the linker script, that can all be replaced. If you don't want to use the default stuff that we are using, you can replace it all. It's just like any other embedded C program. It's set up to take the default stuff by default, but there are ways to override every one of those things that you're mentioning there. You're saying, are there any pointers to that? I don't know that Intel has any specific documentation that shows how to do this, but if you were to just like Google typical GNU compiler types of topics, you should find general purpose GNU references that describe how to replace all of that stuff. That would probably be the best pointer that I could think of there.
There's a last
So,
question, from Ivan. It says, I was wondering whether the custom instructions could be a danger to security features in the processor, of the processor.
Yeah, so there are no real security features of a Nios 5 processor. Custom instructions are given 2 operands to work on that come from the register file. And so the instructions expose the contents of the register file to the custom instruction logic, and then the result that is produced by the custom instruction is fed back into the register file and dumped into the data destination register. So I mean, you know, I don't know. I don't know that I can think of any security issues with doing that. But then again, Nios 5G doesn't have any specific security features that I would be concerned about. So I don't know that I can think of how that would be too problematic. Custom instructions, they're not the kind of thing that you can not think about. I mean, you absolutely have to think about what you're doing with your custom instructions, right? But at the end of the day, they take 2 operands in and produce a result out. It's a little, I'm trivializing it a little bit. There's actually a little bit more data that you have access to, but there's nothing that I can think of that that would like be of a security concern there. So I would say no.
Just a quick question. Is it probably better to use, if you have like a concern about custom instructions, probably use /m. I don't know the purpose of your project with Nios 5, but could it be a possibility, Rod?
Well, the thing is custom instructions are something that you have to intentionally add to the Nios 5 core.
Yes.
So if you don't add custom instructions, then there are no custom instructions.
Okay.
Yeah.
Okay, so there is another question here. It says, in the new FPGAs, could you use Nios 5 processor? They're talking about Liberty Mesa.
Yeah.
And I also had a question regarding, will Nios 5/G will be supported in standard Quartus soon, in standard edition, because it's on Pro right now, right?
Yes, the Nios 5G is in Pro now, and it should be picked up in the next standard release, which I think will be 23.1 standard that comes out, I think, in the fall of this year. So yeah, this 5G core should show up in standard in the next release. And these cores, all of these Nios 5 cores should work in all future FPGA architectures that we come out with. So like when Liberty Mesa shows up, I would expect it to support Nios 5. And all the variants potentially. Now, some devices might be too small to like actually implement some of the Nios 5 cores that require a whole lot of resources, but like they're, in general, Nios 5 should be supported in all of the FPGA architectures that we come out with moving forward.
Okay. And then it says from Anbin, it says, I see Nios 5/M, basic X and Y, or X or logic and or calculation. Not sure if there's any change for Nios 5G. I think it's related to the previous question, right?
Yeah, as far as I know, that was not fundamentally changed when it went to 5G. I believe that the 5G ALU is built upon the design choices that were made in 5M at the time. Again, I'd have to dig into it and find out the details to that answer.
Okay, perfect. Maybe we can return to the presentation. Do you need to move to the next slide?
Sure, yes. Let's I think we were, let's go to this slide, yeah. So when you're defining custom instructions for a Nios 5G core, there's this hardware and software table that you have to fill out to kind of give the hardware tools information about the instructions you're adding, and also give the software tools information about what instructions are available so that we can create macros and whatnot for the software space to leverage the hardware instructions that you're adding. So the next couple of slides are going to kind of get into what these hardware and software tables look like and how they come together. So let's go to the next slide. All right, so the hardware table here is where you define what opcode you want to associate to a instruction. So as we said before, there can be one of 4 custom instruction opcodes that you can associate to. So in this table, you can select in the opcode thing, you know, custom 0, custom 1, custom 2, or custom 3, okay? And then under func 7, you define how you want the bit pattern that's represented in the upper 3 bits of func 7 to further decode the demultiplexer that we create to generate the custom instruction interface. Okay. Now, if you think about it, this table can have a maximum of 32 entries in it. If you defined every custom instruction and func 7 combination that was legally possible, you would have 32 of these things defined. There could be no more. Okay. Realistically, you're going to do things like this table shows, where instead of defining each bit of the 3-bit pattern, you're going to put some X's in, which mean kind of like, I don't care. I don't need the hardware to decode this for me. Okay. And so when you're defining the func 7 bits, you can set each bit to either 1, 0, or X. And if you set it to a 1 or a 0, that means that you're specifically trying to set what that bit should be to influence our demux. And if you set it to an X, you're telling us that you don't care. You're gonna use those bits in your instruction maybe and do some decode, but you don't want us to further decode that in our hardware. Okay. So if you look at the table just to the right, where your laser pointer is, if it just to the right, you can see that there's a custom instruction 0_00, a custom instruction 0_11. If you look at the table on the left, you'll notice that those names are forming up exactly based on what the opcode and func 7 bits were there. So for every interface that you define in the hardware table here, a custom instruction manager interface appears on the physical hardware perimeter of the Nios 5G core. Okay, so when you make these entries in the hardware table, you are explicitly creating a hardware interface for you to connect your logic to on the processor core. Okay, that's how this all starts to manifest itself. So if you don't define any custom instructions, you don't get any custom instruction ports over here on the hardware. If you do define custom instructions in this GUI, then you'll start to actually see physical interfaces show up that you're intended to plug your custom hardware onto. All right, so maybe let's go to the next slide. Okay, so this is talking about the software table. Okay, now this takes information that you put in the hardware table. So the first 2 columns in this table are intended to be the same values that you would have put in your hardware table, because they allow us to identify, okay, this software entry relates to that hardware instruction that you define in the hardware table. Okay, but then what we do is we give you access to the extra func 7 bits, the 4 bits of func 7 that we don't use for hardware decode, and the full func 3 set of bits. And again, you can plug a 1 or a 0 or an X value into any of these bit positions and tell us how much decode you want for those. But in this case, the decode doesn't refer to hardware, it refers to software macro definitions. Okay, so if you do something like the first instruction here, where you define zeros for all of these things, if you look at the table or the list of instructions on the right side, you'll see that we define a custom instruction macro over there, where you have fully defined what the func 7 bits are and the func 3 bits are. So that macro does not allow you to change those. We hard code those into the instruction because you've defined them in this table here for us. Okay, but if you look in the third instruction here, we basically put X's in those places. If you look at that macro definition where she's got the laser pointer now, you'll see you can pass value 1 in, value 2 in, and an F3 value and an F7 value. And so you have total control in when that instruction gets called, how F3 and F7 get set. So you can pass that information into your custom instruction in a very custom fashion here. Now, the one thing that I would point out, and it's kind of hard to get from if you're not familiar with the assembly language syntax here, the value 1 And the value 2 operands, those can be basically any variable in your C code. Those are just coming from registers. So they can basically be any variable in your C, can be value 1 or value 2. But the F3 and F7, they have to be fixed integers. They have to be constants. Okay, so you can't say like, I want my F3 to inherit the value of variable XYZ. It has to be something that resolves in compilation time down to a fixed integer value. Okay, but so it's not as flexible as you might want it, but you do have the flexibility of changing that constant to be whatever you want on that particular invocation of that instruction. Whereas value I and value 2 can actually just come from any variable in your program, can actually become those values. So this is just trying to give you an idea of like, when you fill out this software table, what you're actually doing is you're impacting how we create the custom instruction macros that you can then use in your program and how those get translated in. And if this looks complicated, it is. You kind of have to read through this and digest it for a little while for it to make sense. But once you kind of, read through it enough and you kind of try it a little bit, this all starts to make sense. Why there's a hardware table, why there's a software table, and how the hardware impacts the hardware ports that show up, and how the software table affects the custom macros that we create for you. And I think I'm going to leave it at that. Let's go to the next slide. So as we said earlier, FreeRTOS is something that we've added to the Nios 5 repertoire inside the BSP generator. So there's a formal argument inside the operating system selection that you can choose. You can actually choose FreeRTOS. So your options are a HAL only, Altera HAL only, microCOS2, or FreeRTOS. And this is, as I said earlier, it's really just for the kernel port of FreeRTOS. We don't have anything that really customizes to any of the extra middleware that would potentially come with a FreeRTOS thing. But FreeRTOS is a nice open source, tiny footprint real-time kernel, often found in embedded systems, and we're just adding it to the list here. So today we support FreeRTOS, microCOS2, and then a third RTOS, which I think is on the next slide, which we can probably go to now, called Zephyr. And so Zephyr is just another open source operating system. It's kind of tiny, but it's built a little bit differently. It's not built like typical bare metal RTOSs like microCOS2 and FreeRTOS. It's actually built more kind of like Linux is built, where there's device trees that define device driver configurations and things like that. Although that doesn't get built into the runtime model of the RTOS, it actually configures the compilation of the RTOS using high-level structures like device trees and all. So Zephyr is actually an RTOS that you can run on Nios 5 today. It doesn't show up in that pick list from the previous slide though, because it's not built as simply as those other RTOSs are, where we can create a very trivial BSP for it and then just compile a very simple RTOS. You actually have to go through a little bit more effort to build a Zephyr RTOS, and the build flow just doesn't fit the model that we use, the way we've plugged in microCOS2 and FreeRTOS and the other BSP generator. So that's why it doesn't show up there, but it does exist. There's an example up on a GitHub and documentation on a rocketboards.org page that defines how you can bring this Nios 5 Zephyr demonstration up on a platform. And so this RTOS exists. So there's basically 3 RTOSs now, right? FreeRTOS, microCOS2, and Zephyr. I don't feel like we're going to make too much more investment in trying to port RTOSs onto the Nios 5 cores. There's obviously a lot of other RTOSs out there that would be able to run on Nios 5 without any problem. I just don't think that Intel's going to necessarily try to make a version of that like integrates into our BSP editor and is demonstrable like that. That could happen, but as of right now today, I think that these 3 RTOSs that you see are going to kind of be it for a while. So let's maybe go to the next slide. So for doing software development and debug, we provide an IDE called Risk-Free IDE. It's been around in the tools for about a year now, for as long as, almost as long as Nios 5M has been in the tools. And this would be kind of, if you want a graphical code development environment. It's an Eclipse-based environment, much like the Nios 2 IDE was for Nios 2. It's based on Eclipse, and the compilers, the debug environment, and everything can be brought up in a graphical representation here. If you don't like using IDEs and graphical environments, just like Nios 2, everything that you can do in this IDE from a development and debug perspective can be done off of the command line as well. You can compile Nios 5 code, run command line debug sessions and things like that right off the command line. So if you like a GUI for your IDE development, the risk-free IDE would be the option available for Nios 5. And I would also just point out, this is only for Nios 5. You can't use risk-free IDE for Nios 2 today. You'll probably never be able to do that. But this is the Nios 5 version of a graphical user interface. And it works over the normal JTAG debug cables that you could talk to a Nios 5 in the FPGA through. So like our USB blasters and things like that are all supported through the risk-free IDE. And risk-free IDE also has debug awareness for microCOS2, FreeRTOS, and Zephyr. Which is just kind of a nice little add-on as well. And then another thing that I would just point out about the risk-free IDE, and it's shown in the actual image on the right side of this thing, it also works with our SoC devices in a heterogeneous debug mode, where you can actually have Nios 5 debug sessions running simultaneously with ARM-based debug sessions. So like if you've got a Cortex A53 and like an Agilex device, and you put a Nios 5 in the FPGA, and you want to do simultaneous debug of both the software running on the ARM as well as the Nios 5, the risk-free environment will actually allow you to do a heterogeneous debug session like that, where you can bring up both debug sessions simultaneously and kind of do co-debugging like that. So risk-free is a pretty interesting GUI that we've got for doing that kind of development, either standalone ARM or standalone Nios 5, or both heterogeneous kind of simultaneous debug, if that makes sense for you. So maybe let's go to the next slide. All right, so there's a number of resources available that you can get example designs up on the Intel Design Store. We've been putting FPGA designs up in the design store for a long time. You'll find a bunch of Nios 5 and Nios 5G designs in the design store. The Nios 5G Zephyr design is actually up on rocketboards.org, but these things are out in the public. You should be able to access these either on Intel sites or on the rocketboards.org site. So there's a bunch of design examples that you might be able to find that are just in the Nios 5 space here already. From a licensing perspective, Nios 5 is licensed a little differently than Nios 2 ever was. With Nios 2, if you wanted to use Nios 2E, you could actually use that for $0 license. If you wanted to use Nios 2F, there was actually a fee for that license, and you had to re-up the license every year or something like that. With Nios 5, it's a $0 license that you do once, and it's perpetually, valid, I believe. I don't believe it ever expires. But you do have to have a Nios 5 license that you can go to the self-servicing licensing center and get for yourself, and it's a $0 cost. And then on the right side, it just talks about more documentation that's available on the Intel website for, there's app notes and user guides and videos that demonstrate how to do various things and more things like that from a training perspective. And I think that's all. Yeah, that's all the slides that we had, right?
There's a question about Zephyr support, if it includes TCP IP stack.
I don't know the answer to that. If it doesn't, it should. It should one day. I don't know if the Zephyr example today actually does TCP though. I know the very, very first thing is just a simple hello world example, and that's kind of what I think is up on the website today. So there's actually
it doesn't right now.
Yeah, but Zephyr does have a TCP stack, and I would think that it's probably on our radar to try to take the hardware that we've got, the microC TCP IP example running on, and kind of do the similar thing with a Zephyr with TCP. But today you're not going to find the TCP example yet.
Thanks everyone. This was great, Rod. I put our Q&A section is open now, and I also added to our chat a survey where you can fill out any comments or in general your impressions of today's meeting. Oh, there's another question from Carlisle. It says, can the AI suite be integrated with the Nios 5?
So
That is our intention.
yeah, what I was going to say to that is the answer is yes, but like it's the way I would interpret that is that you can obviously you could take the AI suite and you could add Nios 5 processors to those system designs that you're creating with the AI suite, and the Nios 5 can interact with those AI suite components, right? But it's not like the AI suite drops into the Nios 5 architecture in some way and enhances the Nios 5 processor in any way. But the Nios 5 can absolutely be integrated with an AI suite component and orchestrate it and drive operations through it, if that makes sense.
Then someone asks about the performance between Nios 2 and Nios 5 on the same FPGA, but I think that question was answered. Do you have any other questions, Rod? Rod comments?
Yeah, so the answer is yes, there is a performance difference. Generally speaking, the Nios 5 pipeline is a little bit higher efficiency than the Nios 2 pipeline. So like if you do a dry stones comparison between like you know, a Nios 5M or Nios 5G versus like a Nios 2F, those are kind of similar. You'd probably find that the Nios 5 variants are going to process that a little bit more efficiently than Nios 2. Now, having said that, they're also a little bit bigger because of that as well. So the answer about performance, though, is yeah, the Nios 5 is a little bit more efficient. It's not like it's 2 or 3x faster, but it is, if you measured it, you would find that it's, maybe 0.5 dry stone MIPS per megahertz versus 0.8 or something like that. It's measurable, but it's not like, blow it out of the water kind of difference.
I think we can do this one last question. We still have 4 minutes to go. Do you recommend any network on chip if I want multiple Nios core on one chip? I think Altera has NOC paper about a decade ago, something mentioned by Richard Ross.
Well, so Platform Designer basically builds its own interconnect out of a network on chip topology. So if you wanted to put multiple Nios 5 cores on the same FPGA design, you could literally just drop them into a Platform Designer system and have the interconnect created for that however you desire, whatever makes sense for you. They could have local exclusive access to peripherals. They could share peripherals. They could share memories. They could have local exclusive memories. Almost any kind of a system topology that you could imagine, you can construct in Platform Designer. And putting multiple Nios processors inside of a design is absolutely something that people have done for decades. And they generally just rely on the generated interconnect that Platform Designer creates for that when they do it. You can build rather complex topologies within Platform Designer and integrate numerous processor subsystems that interact in very complex ways, if you like. And so that's generally what people would do. Aside from the Platform Designer, generated logic, I don't know that I would recommend any other kind of network on chip IP or anything. The generated interconnect out of Platform Designer is usually totally acceptable.
Thank you. Thank you, everyone, for attending. We still have a couple of minutes to go, but I will wrap up the session. Thank you so much for your attention, for attending this meeting, this Ask an Expert webinar. Thank you, Rod, for your sharing today, for your expertise. A feedback survey link has been placed in the chat, as I mentioned, and you'll also soon receive an email with the same survey link and the recording of the session in case you want to go over the slides again. The meeting will short closely and we'll close. Sorry, we'll close shortly. And thank you all for attending today.